The final speaker is going to be Dr. Euan Allen, who's an EPSSC Doctoral Prize Fellow at the University of Bristol. And his talk is entitled Quantum Optical Metrology of Correlated Phase and Loss. So, Euan, whenever you're ready.
Oh, thank you, Jorge. Yeah, thanks everybody for tuning in, and thank you to BQIT organisers for putting on a really great conference, and also for inviting me to talk in front of all of you today. Apologies to those at Bristol who have already seen this talk in the practice for BQIT, so maybe you can go and grab a cup of tea. But I'm going to talk about some work that we've done recently on finding optimal bounds and in metrology when you're measuring correlated systems of correlated phase and loss. So yeah, this work was done in collaboration with this set of 5 people. Patrick actually led most of the effort in the work, did most of the nasty theory, and lots of these other guys. Tom kind of has the background in atomic systems, and I go into how that relates later. But yeah, all these great people collaborated on the work, and it recently got published in PRL, so you can go and read all the details there if you want to find out more. So we're going to talk about quantum metrology, and I'm going to go into now what that really means. So in the broadest sense, what is a sensor? So we're going to have some probe state, which we're going to prepare, and then we're going to send it through some process which we'd like to know about, and then we're going to measure that thing and hopefully learn something about this process. There's a few things you might care about when you do that. One is the accuracy with which you can do that. So that's how close you get to the true value of that parameter that you're interested in this process. And one might be, if you then take repeat measurements, how distributed are those around that mean value? So that would be the precision, as we would call that. And what we care about really is there's 2 things you can do to increase the precision. One is to increase the variance on any particular measurement you make. So for one particular measurement, you can increase the variance, or you can just measure lots and lots of times. So you just send in, you take repeat trials, or you send in more photons. And really, quantum metrology, in the sense that I'm using it today, is the quest to minimize this variance here, this single measurement variance, for cases when you can't really do repeat trials, or when at least increasing the number of photons you put into your system is not possible. So you can't just increase it arbitrarily. So yeah, if we look more generally at what a sensor might be, then you can see that there's going to be some initial state preparation. We're going to send it through this dynamic process that we care about. That's going to produce a final state. And then we're going to take a measurement, and using outputs of that measurement, we're going to construct an estimator to guess what this parameter is, this parameter chi that we're interested in. And how do you define how well you can do that? How much the precision of that thing can be bounded? So you use this equation. The first inequality here is this thing called the classical Kramer-Rao bound, usually just called the Kramer-Rao bound. And the important feature of that is it really optimizes over this estimator. So it tells you the optimal precision you can get on your estimate when you're allowed to optimize over this estimator here, but you still need to define a measurement for this thing. This is why you have this big M here, which is defining the measurement. This second inequality here is something called the quantum Kramer-Rao bound, which actually allows you to also not only optimize the estimator, but optimize the measurement, because we have measurement theory in quantum mechanics. So you can optimize these 2 things. And actually, if you further parameterize certain aspects of the quantum Fisher information, it actually allows you to optimize this entire system. So it really gives you the ultimate bound you can get for any input state, any measurement, and any estimator. So it's the bound we're using here. And you find this thing called the Fisher information, which is this thing here, which bounds this variance on this estimating this parameter. So this is the metric we're going to use, this quantum Fisher information. So there's been lots of work looking at how we can, finding bounds, and also working out how we can experimentally saturate these bounds in sensing systems. I can't go through all of the list of works, but there's some great work looking at bounds in loss estimation and more generally with Gaussian states here. And also there's been some great experimental work looking at actually saturating these bounds. So some work looking at estimators that actually allow you to improve precision and the accuracy of your measurement at the same time. There's this great work here from Ulrich Anderson's group, which use optical they use feedback control of their squeeze states to increase the precision with which they can measure using squeezing. And finally, some work from Bristol where they used twin beam states, so effectively Fox states, and did some raster scanning microscopy with a transmission measurement. And they showed that, yeah, using this correlated down conversion source actually gives you improved precision over just a coherent state and attenuated laser. And so you can see the improvement in the precision quality, in the image quality shown here. There's also been, so previous slide was on single parameter estimation. There's also been a kind of plethora of work on multiple parameter estimation, where now you don't just have one channel with one parameter, you maybe have a set of channels which each have their own parameter of interest that you'd like to measure. And this thing could be applied to, you know, sensing networks or imaging systems where they're different parameters. And yeah, there's a whole lot of work looking at kind of finding those bounds. And more recently, there's been some interesting experimental results coming out of this area. And we're kind of interested along these lines. So in fact, actually more interestingly, interested in this result, where they looked at the limits of estimating both phase and loss within an interferometer. So if you try and estimate these things simultaneously, what happens? And there's actually found to be a trade-off between these two things, where if you try and simultaneously estimate the phase and loss within an interferometer, then you can't saturate the quantum Cramer-Rao bound. So there's no practical strategy of actually saturating this ultimate quantum bound. And the intuition really is kind of that to optimize the information that you get on phase, you kind of actually can't simultaneously optimize the information you would get on loss. So they actually require different states and different measurements. So optimizing them both at the same time for the two parameters that you're interested in isn't possible. And so you can't saturate this Cramer-Rao bound. But there are a lot of systems where, so there are a number of systems where you do get phase and loss implemented in the beam. And actually, many would argue that there's most systems actually give you phase and loss, because there's this thing called the Kramers-Kronig relationship, which says that any loss or transmission is often accompanied by a change in refractive index, and so that would impart a phase shift. Examples of this include things like atoms, so atomic systems. So if you're looking at rubidium atoms, then this thing will impart a loss and a phase simultaneously. And if you're, say, doing sensing on a ring resonator, if you're firing light across this bus waveguide, and you care about, so these are just parameters of the ring in themselves, then actually this ring applying to this node will impart some transmission and some phase, dependent on these parameters. And the important thing here, so not only are these imparting phase and loss at the same time, but they're actually correlated. So in some sense, there's a relationship that actually relates phase and loss to these underlying parameters which you care about. And so the question we really looked at this work was, does actually having access or the fact that these phase and loss parameters are correlated in some way, does that change how well you can saturate this bound? And that's what we looked at. So the system we look at now is slightly changed. So we've gone back to a single mode, but now we have these two, this phase channel and this loss channel being applied to this overall thing. And what we are interested in is this underlying parameter chi, which drives the phase and the loss imparted onto this node. And then we're just going to make a measurement at the end. So yeah, this capital lambda here is just describing this overall channel, and the kind of operations are defined on its operations on a coherent state. And we call this just correlated phase and loss estimation. This includes, so this kind of setup includes a number of things that might interest people. There's the case where actually maybe the loss isn't dependent on, sorry, I should also say that this eta defines the transmission. I'll probably use loss and transmission interchangeably, but it actually strictly defines the transmission. So yeah, the case where the transmission doesn't vary with this underlying parameter is just the case where we've got, you know, lossy phase estimation. So where there is a loss present, but actually you're really just measuring, you're interested in the phase because that's what your parameter is driving. And there's also cases where the opposite, where you're applying a phase, a fixed phase shift, because it doesn't depend on this parameter of interest, but actually what you're interested in getting information from is from the loss, because that is where the parameter is driving it. I've called this phasey loss information estimation, but it's really just usually called loss estimation. And for what I'll discuss today, we assume that the relationship between these two things, so the functions that drive these two parameters, is known. But we do also look at cases in the paper where actually you don't know this underlying relationship, which we call direct absorption estimation, which I won't go into today. So I'll stay in the regime where we actually know this underlying relationship. So how do you go about proving bounds in these kind of systems? I'm not going to go into the detail, but we kind of use results that are derived from this Nature Physics paper, which is a really great result. So the problem with loss, so quantum Fisher information is quite nicely well defined for pure states, but of course now our channel is implying a loss, and so we no longer have a pure state at the output. But there was this result that showed actually if you have this channel that we're interested in, which is a function of our parameter, then to find the quantum Fisher information of that channel on this parameter, all you need to do is do a channel dilation. So you consider more modes than you have in a larger Hilbert space and consider a unitary operation on that larger Hilbert space, which includes your modes and some environmental modes. That unitary is here, and you've got your state and your environment. And the act of the unitary on just your state modes is the same as your non-unitary channel. Then actually, if you just minimize over those possible unitary dilations, the quantum Fisher information, then you can actually find the Fisher information of this channel here. So this is the technique we use. We do a dilation using this unitary, and then we effectively minimize the Fisher information, quantum Fisher information here to get the actual quantum Fisher information of our channel. So we can do that for the one that I showed previously, where we have this correlated phase and loss. And you get to something like this, where it depends on the mean number of photons at the input, the parameter, the transmission parameter here, and the dependence of the phase and the loss and how it changes with the parameter of interest chi. So a few things to note is that the quantum Fisher information here is only dependent on the mean number of photons in the state. And so actually it bounds all states. So because it's not a function of any particular feature of the state, apart from its mean photon number at the input, then it actually bounds, it optimizes over the state simultaneously as well. So we kind of get this for free. So this is actually the fundamental quantum bound, which is what we defined as this Q subscript chi here. So this is the best you can do with any quantum state, any measurement, any estimator. And also what we found is actually this is just the sum of the information you would get from loss estimation, estimating the loss individually, plus the information you would get from estimating the phase individually. And this seems to flag up again the result from the Oxford group, where actually your intuition would say that you can't simultaneously saturate these two things at the same time because of the benefits that each of these things require from the state. They're opposite. So this at least seems like a bound that you shouldn't be able to saturate. So we now have our bound, and we want to maybe find a strategy that actually goes and saturates that bound. And so I'm going to kind of almost tell the answer at the beginning, and then we'll work it, out and show that it is optimal. But in the paper, we kind of go through why you might think this is the case. But if we now look at how this channel acts on a coherent state, so now I've just got my quantum optical phase space, and I've just drawn coherent states for now. If we send in a coherent state here, so the first thing it's going to do is apply a phase shift, which is a function of this parameter. Again, this is the parameter we're interested in. And then you're going to apply some loss. We'll go through this transmission. And so the overall vector that you move in this space, you can define by this black line, which I'll just label as chi. And so you might think, okay, this is really what I'm interested in, is actually the length of this parameter. So maybe what I'll do is I'll want to finally make a measurement where the squeezing is along the vector that I'm interested in, which in this case would mean you'd have to start with some squeezing along this vector because it would slightly get rotated as you went through the phase shift. And then you want to homodyne along this angle to know what this vector is. So this is the measurement we considered and the state we considered at the input. And we also, to slightly simplify things as well, just because sometimes you can come up with dependencies on kind of fine features of these states. Thank you, Jorge. we actually only considered the information held in this displacement vector, so in the mean value of these parameters. So looking at just this displacement, the information contained in this displacement vector, which you can get from homoline detection, you find that the bound looks something like this, where now this is the mean number of photons at the input, this is the mean number of photons from the squeezing in your input state here. And then we have the same parameters as before, and then this R parameter also is a function of the number of a function of the squeezing at the input. You can define the squeezing in this way, and so we actually maybe want to look at how close this information gets at it's saturating this quantum bound here, and you end up with something that looks pretty messy. But if we plot this, so now we're plotting the ratio of this information on our squeeze state strategy against the optimal quantum limit, then as a function of the transmission, the loss parameter, and changing the amount of photons in our input state, we see that we can, I should know actually, sorry, the squeezing is also a function of the number of photons at the input. So there's an optimal squeezing amount that you can apply to this state, depending on how many photons and the transmission, basically. So this thing needs to be optimized somewhat, depending on this input number of photons. So with each of these lines, we're changing the amount of squeezing in this state. You can see that actually this displacement, the information in the displacement vector, it's pretty close to the quantum limit. So even in cases where we have kind of 10 to the 3 photons at the input, we actually are already above 80, most of the time above 80% of the information you can gain kind of absolute. And just as a reference, because I'm aware that these functions aren't clear, or it's not easy to work out what exactly is going on with these functions. If you have 3 dB of squeezing and a transmission of 80%, which puts you here, you sit on this line. So you effectively sit above 90% of getting the optimal quantum Fisher information. So it seems to be that this displacement vector actually not only saturates this bound, which we were pessimistic about earlier, but it allows you to do it with pretty reasonable resources and get pretty close. So just a summary of some other aspects of the work we go through in the paper. If you apply, so previously people have looked at actually, if you have access to a phase shift and you're allowed to apply it multiple times to your state, then you can actually get pretty close to the quantum limit using just this multipass strategy and a classical probe. We show that actually this is true in this case as well. So by applying our channel multiple times to the same mode, which including a phase shift and a loss, you actually are able to reach 60% of the quantum limit just using coherent states. So it actually seems to be that access to these multipass strategies means you can get pretty close without having to use these quantum states of light. And then we go on to show that, so if you assume bright states, then the bound in this displacement vector actually simplifies to this thing, where now we just have the loss, transmission, and the squeezing parameter here. So, and this is the quantum advantage, sorry. So this is the ratio between coherent states to these ideal squeeze states. And in both cases where the relationship is known, correlated phase and loss, and unknown, everything seems to simplify to this. So actually this bound seems to be kind of driving everything, even in cases where you do and do not know this relationship. And just a note on practicality, because I'm an experimentalist, so maybe you want to base this in an experiment. So we compared this to actually some single molecule experiments. So this is all data all values taken from a single molecule experiment. If you have 10 microwatt beam, about 633 nanometer light, and a total transmission of 95% in your experiment. If you input 15 dB of squeezing into that, and we assume you don't know the phase loss relationship, then compared to a coherent state, you reduce the mean squared error of the fluctuations by 12.5. So you get an order of magnitude improvement, and you reach 80% of the advantage you would get from using Fock states of an equal brightness, effectively. So you do pretty well using this squeezing strategy. And with that, I'd like to say thank you, and yeah, any questions are welcome.
Thank you, Euan. We have some questions coming in already, but as always, I would like to start with mine first. Based on your presentation, can you venture what would be the optimal or the worst medium for quantum optical measurements, and how does that depend on the type of light used?
The worst medium in terms of like which one would be most difficult to probe with a quantum?
Correct.
Source. Yeah. So I think in general, I mean, so this parameter, which I mentioned, so this transmission parameter includes not only the loss imparted by the sample that you care about, but also loss imparted by, you know, anything else that exists in your experiment. So if you've got a big gas chamber cell, say, and there's lots of loss at the facets of that, in classical light, you can just kind of calibrate that out, and it doesn't really affect your measurement, whereas quantum states get severely degraded by this. So yeah, generally any samples which have lots of co-propagating loss, which you can calibrate but actually isn't a function of the parameter you care about, that's bad. And also, I guess, would highlight that Jake Yelly has, we're looking at also samples that saturate tend to be pretty, actually degrade quantum and classical poorly as well. But I would yeah, want to highlight that work as well. So check that poster out as well.
All right, thank you. So a question from the audience from Samir Vartak. Can you please give examples where increasing number of photons for measurement is not possible?
Sure. So I think, yeah, so I just mentioned one. So if you're looking at a gas and it saturates, then which is actually something that Tom brought to mind. So if you're looking at, yeah, atomic systems and atomic gases, then if you turn up the laser, then eventually you run out of gases that atoms that can absorb light, and so you start to degrade the amount of information you get, which is actually what, yeah, Jake's poster is about. Another one which people quote commonly is biological measurements. So you might either alter how biological systems act or kill them completely. And I guess maybe if you're thinking about LIGO and also other systems, then actually sometimes turning up your laser, although it reduces the shot noise, so it gives you more statistical information in terms of sampling, it might actually give you increased technical noise from, in the LIGO case, it actually back action on the mirror increases that. So there's a number of, yeah, examples.
Good, thank you. Another question from the audience, Maria Chechova is asking, how does the detection efficiency affect that measurement?
That's a really good question. For the phase and loss example, we haven't actually looked at how detector efficiency degrades. I think actually I would expect it to be that it would, if I can get this, this is, yeah, so in general, it's, so if you, so in general, quantum state probing systems with quantum states is done, you get the most improvement for small absorbing samples, so samples that don't absorb much light. And so actually, I think the advantage you get from, say, having a total system absorption from the sample that is 50%, that gives you a certain improvement, which you can work out using this equation. Would be the same if you had a sample that was maybe weakly absorbing, so much less than 50% absorption, but then the detector efficiency pushed the total absorption up to 50%. So I think it would kind of, you can kind of, this ITER encapsulates all absorption events, including things like detector efficiency, I would think, but we haven't formally looked at it. But that's certainly the case in direct, just plain absorption estimation.
Thank you. We have time for another one or two questions. So one from Jason Mueller. What are your constraints on choosing an estimator to satisfy the Fisher information bounds? For example, eta constant is a very precise but very useless estimator.
What are your constraints on choosing an estimator to satisfy the Fisher information bounds? Right, I see. So if you, I think so. I'd have to. Yeah, I think so. In the paper, it's estimating the length of that vector, which I can. So we do define the estimator, which is the length, the measurement of this length of this vector. There's subtlety in actually this vector, which defines the squeezing angles and the Hodine measurements you want to make, is actually based on the parameters that you're interested in. And so if you don't know those preemptively, or at least know them to some precision, then you can't actually do this optimization. And so you maybe have to do this optimization on the fly, which is what the student George is looking at the moment, is actually in cases where you have no idea what the phase and loss is to begin with, then you actually need to start with coherent states and then slowly do some updating as to optimize the measurement and the thing to learn what this vector is. But we do define an estimator in the paper.
Thank you. And a final question from Alex Clark. What kind of molecule do you consider for the final calculation?
So I can't remember the paper exactly that I don't have the reference in which I should have done actually in the slides. It was from Phil Kukura. So, and I don't think, I mean, it's kind of independent of the type of molecule. All we really care about to do with the actual sample itself is this transmission parameter. And these values really, so these values define the number of photons in terms of the coherent state or the coherent amplitude. And then this transmission is what the sample is driving really. So really you can have any molecule, as long as it fits within this transmission window, then it would be appropriate for this calculation.
Thank you. And with that, we've exhausted the questions from the Slido list. So please, if anyone else is interested in asking further questions, go to the corresponding channel. So thank you, and again.